Section 14.1 talks about functions of several variables. So pretty much it talks about 3 dimensions, 4 dimensions. Anytime you see, we're used to seeing y equal f of x. So f of x is really y. And if you see f of x, y, that really means nothing more than z. So this is saying z equal 1 plus x squared over y squared. If I wanted to evaluate those, if I wanted to evaluate what is f of 1, 2, that is 1 plus, wherever you see an x, you replace a 1 and a squared. Wherever you see a y, you replace a 2. And f of 1, 2 would be 1 plus 1 half, which is 3 halves. So basically what this is saying, the point 1, 2, 3 halves would be on the graph of this z surface. And if I wanted to evaluate what f of 0, 5 is, that would be 1 plus, and again the same deal. I would take the 0 and square it over the 5. F of 0, 5 would be 1 plus 0, which is pretty much 1. So again, what this means the point x equals 0, y equal 5, and z equal 1 would be on the graph of the surface z equal 1 plus x squared over y. Now, the rest of this is a bit of graphing, 2 dimensions for the most part, but there is something that we need to get out of the way. Graphing is not always an option. That's because they might give us something we can't graph. We don't know how to graph. But we need to figure out a lot of things just using the domain. So if you glance at this problem, here, example 2, it says, sketch the domain of f. We just want the domain. And the domain applies like traditionally. If I see an even index radical, the radicand, the quantity underneath the radical, must be bigger than or equal to 0. If I see a fraction, the denominator cannot be 0. And if I see a log, the argument of the log must be strictly bigger than 0. In this case, when I glance at this, I notice that's an even index radical. I would say the domain is 9 minus x squared must be bigger than or equal to 0. And if you think of this as a graph, that's an upside down parabola crossing at negative 3 and 3. It's bigger than 0. That's when x is between negative 3 and 3. So when it says sketch the domain, since this is f of x, y, the domain is x and y. When I say x is between negative 3 and positive 3, 1, 2, 3, and 1, 2, 3 included, and wouldn't you agree that the domain would be, since there's no y, any of this will do? Any point between those two values will work? Now I'm going to get the 3D graph for this. I sketched the graphs of all of those and I saved them already. And that's really how it looks like. If you look at the 3D graph of this, and keep in mind on the GeoGebra or Desmos, wherever you use, you could rotate this any way you want. And since I knew exactly what I wanted, I rotated. Do you see where I put the x-axis? I put it almost flat. And do you notice this graph is shifted up 1 unit? And do you notice that if I look at the x, it's not going to exceed positive 3 and negative 3? And this shaded part that I shaded is really right there. If I get to the next problem, again, I see a radical. You're going to either see a radical, a log, or if I see a radical, I say, okay, well, let's see. Then x minus the domain. X minus y must be bigger than or equal to 0. What does that mean? That means y is less than or equal to x. Y equal x is a solid line cutting at 45 degrees. Y is less than, don't you shade below? So the domain would be any value beneath that line. And I sketched a graph of the 3D for that as well to show you how it looks. And this is what it looks like. So if you notice, again, I'm able to rotate this any way I like. This is the positive x, this is the positive y. And do you see this is in quadrant 1? That's like quadrant 1. And do you see that you're going to shade toward the negative y? And the shading is pretty much right there, which matches what we have. So you're not responsible for the 3D graph. Keep in mind, this is what we're going to do later on. We're going to figure out a lot of things about this graph just by looking at the domain. Same thing here. How about this graph? Well, this one we know. If I take 4x squared plus y squared minus 16 and say that must be bigger than or equal to 0, this is saying 4x squared plus y squared must be bigger than or equal to 16, or x squared over 4 plus y squared over 16 must be bigger than or equal to 1. So 2 in the x, 4 in the y. I know that's an ellipse. When you say it equals, you're on the ellipse. When you say bigger than, you're outside of the ellipse. And when you say less than, you're inside of the ellipse. So you're really trying to mimic that. And if I look at the 3D graph of this, again, this is all they want in the section. But if I look at the 3D graph of this, it's right there. And you would notice there is a longer stretch along the y than there is on the x. Now I'm going to change this problem just because I'm sick of the same thing. Let's say we're doing natural log. There, make it better. Well, if I want the 2D, I'll say, okay, domain. I'm taking the log, take the quantity underneath the radical. I'm sorry, take the argument and set it to be strictly bigger than 0. Doesn't that mean that x squared plus y squared, if I move those to the right, that will be less than 9? That's my domain. I'm done. Graphically, what does that mean? Well, graphically, that's really simple. You're looking at a circle with a radius of 3. 1, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, 3. And if I sketch a graph of that, that's a circle right there. When I say x is less than, so equal I am on the circle, greater than I'm outside of the circle, less than I'm inside of the circle. Well, if I look for the 3D graph, the 3D graph look, oh, by the way, I forgot to mention. That's dotted, right? That's not included. And if I look at the 3D graph of this, well, that looks like this. So if you look at all what we're doing, we're looking at the shadow on the floor. There's X, there's Y, and you notice that's a 3, that's a 3. And if I look at the shadow on the floor, that's all I see. Same thing here. If I look from the top, the only thing I see would be a hollow on the inside, and the shading will be on the outside. Next problem up. If I look at this and say, what's the domain? Well, this is a radical. X squared plus Y squared must be bigger than or equal to 0. And what does that mean? Let me think really quick. Okay. X squared plus Y squared are bigger than or equal. That's everything, isn't it? That's everything. Right? They equal 0 if X is 0 and Y is 0. And no matter what you pick for X, no matter what you pick for Y, that's going to be bigger than or equal to 0. So the domain is really pretty much all real numbers. There's no restriction. Oh, I didn't pay attention to that. Let me see what the graph of that looked like. The square root of X squared plus Y squared. Oh, yeah, I know. It looks like what do you call it? A cone. Right? Let me see. Did I graph that? I did. You know what? I never paid attention to it. You know, I made these problems up, so I didn't know what to expect for the most part. So, if that's the graph, then yes, that makes sense. There it is. If you look from the top, do you notice that the shaded part from the top, you're going to see the whole thing shaded? There's no restriction there whatsoever. And then that kills, I gave you part F for that reason specifically. Right? I gave part F as a cube because just for that, you know. So that one has the same deal. If I look at the domain, well, that's a cube root. It's all real numbers. There's no restriction. Pretty much, you're everywhere. And I did the 3D graph. I mean, we really don't need it for this problem. You don't need it for any of these problems. But here it is, since I already did it. And it looks like this. Alright, now, again, you're not responsible for the 3D graphs. They're only there to kind of show you what's going on. You are responsible for the following 3D graphs. What's a contour graph? We say level curves or contour. The level curves of a function f of x, y, remember that means of z, of two variables are the curves with equation z equal k, where k is a constant in the range of f. So pretty much this is what they say. This is how they start the problem. I'm going to elaborate on what that means. It says draw a contour map of a function showing several levels. What you do, they say, set this equal to k, just like they did right there. But if this is z, aren't you really setting z equal to k? And then they say take k equals 0. You get x squared plus y squared equal 1. Sketch a graph. K equals 0. Okay, I'll get it, don't worry. Isn't the only solution x equals 0 and y equals 0? You label that. What if I let k equal 1? Doesn't that mean really you're letting z equal 1? That means x squared plus y squared equal 1. Isn't that a circle with a radius of 1? And you label that k equal 1. What happens if, and again, since I know it's a circle, I could go for 2, but why not go for 4? Why? Because I know circles work best if I have perfect squares. K equal, isn't that z equal 4? Right? Now we know that k cannot be negative. So several levels right there. Now, I am adding to this. I'm elaborating on what they mean, and you should do both. If I look at the graph of the 3D, if I look at z equal, and we know what this graph look like, and that you're responsible for that graph. If I look at this graph, keep in mind what I'm doing. When I say let k equal 0, I'm saying z equals 0. Isn't that the floor? Doesn't the floor touch at one point only, which is the origin? If I let k equal 1, isn't this saying really let z equal 1? If I let z equal 1, aren't you cutting a plane right there? And wouldn't this plane intersect this at that circle? If I say let k equal 4, doesn't that mean I'm saying let z equal 4? Z equal 4, if I go up to 4 and I sketch a plane, shouldn't that intersect, creating that right there? So when we say level curves, we're taking the 3D and we're running flat, just parallel to the XY plane. We're just running a bunch of z's. And I could show you really quick. X squared plus y squared equal k. Right? Z equal x squared plus y squared. So if I go to my website, the one that we mentioned, GeoGebra, or Desmos, and if I input z equal x squared plus y squared. There it is. Now, if I say z equals 0, do you see if I turn this, they only touch at one point right there? What if I say z equal 1? That's the value of k. Notice where those intersect. Do you see the circle? It's right there. What if I say z equal 4? Do you see that when I chop this up, look at from the top, that's what I see? So that's really what it is. Now, contour graphs, you're really after this. How about this? Well, again, they only want the contour graph. What they want us to set this equal to k. If I have x squared y equal k, doesn't that mean y equal k divided by x squared? Now what? When I say let k equal 0, isn't that saying let z equal 0? Because that's what z equal, and you only replaced z by k. Well, doesn't that mean y equals 0? How does that look like? Oh, I'm sorry. Here we go. I didn't put the grid, I should have. So if I say y equals 0, this is k equals 0. How about if I let k equal 1? Doesn't that mean y equal 1 over x squared? How about if I picked k equal 2? So at 1, I am at 2. So it's a graph that looks like this. What if I let k equal negative 1? Doesn't that mean that y equal negative 1 over x squared? And how about if I let k equal negative 2? Doesn't that mean y equal negative 1 over 2 over x squared? And that's all you have to do. In this case, you don't need the 3D graph. But if I look at the 3D graph I did, it's kind of hard to see. It looks like this. And I will elaborate on what that means in a minute. Notice if I run z equal 1, it's going to intersect this graph up there. And where's it going to intersect? It's going to intersect at the circular part of this. I know you can't see it. I could show you that really quick. So if I go back to that website, z equal x squared y, z equal x squared y, there it is. It looks like this. Do you agree that if I cut z above, z equal 1, do you see where the blue and the red intersect? Do you see the shape they intersect on? And you know the quadrants look like this, positive and negative. So that's what? It's mapped around the positive, and if I let z equal 2 or 4, I'm getting that shape right there, and that shape right there. And if I let z equal negative 1, guess what I'm going to get? I'm going to get the bottom below. Do you see below it matches as well? So this is looking at the bottom. And what do you notice? The intersection is actually right there. And that's what it is. Alright? And one more I have for you. If I wanted to sketch a graph of, if I set this equal to k, this is really saying y equal k over cosecant of x, or y equal k the sine of x. Well, I know what that looked like. If I take k to be 0, y equals 0. If I like k to be 1, y equals sine of x. If I take k to be 2, y equals twice the sine of x. And if I take k to be 3, and make sure you label those for me on a test, that's what I need. This is 3, this is 2, and this is 1. What if I go for negative 1? Y equal negative sine of x. That looks horrible. And what if I go for k equal negative 2? Y equal negative twice the sine of x? Much nicer. And there it is. And if I look at the 3D of what that looked like, y equal the cosecant of x, the graph looks like this. Again, you're not responsible to know this graph. And if you really glance at this and pay attention to the z equal, when I cut with a z, with a plane, it's going to intersect, and let me show you what that looked like. This will be the last graph. Let me take this one out, and we said we want z equal y cosecant of x. And this is really what it looks like from the top. But if I go on the side, okay, I can't seem to get the side. I'm stuck on the, okay, here we go. That's really what it looks like. Actually, the positives are like this. So here it is. It looks like a sheet running continuously. Oops, I rotated, I didn't mean to. Okay. One more time, sorry about this. Okay, here we go. It looks like a sheet of paper running, see, one sheet of paper, and you have it this way. If I had z equal 1, oh, it's upside down. Okay, I could fix that. Okay, oh boy. There. If I had, it had z equal 11. I meant 1. Okay, there. If I had z equal 1, do you agree that the intersection right there looks like a sine? If I rotate it and look at it from the top, do you see the sine right there? Right? And there it is. So you take that continuous piece and you just chop it, and this is like the sine wave running across of it. Alright? There is definition in the book, you need to read it. Definition about interior points, boundary points, interior region, open region. It's not going to be on your test. It is mentioned in a few definitions and terms. You should just familiarize yourself with it, just to understand what that means. And at this level, hopefully, you'll get that no problem. And that would be it for this section.